The broadcast is now starting. All attendees are in listen-only mode.
Okay, good afternoon, everybody. Thank you for joining us today for this discussion on timely alarms. So, for those of you who may not know who Mac Solutions are, just a very quick introduction. We are the creators of the ProcessVue Alarm Management Suite of software, which, according to a recent ARC study, is the most popular independent alarm management software as used in the European power generation market. So, which is something we're quite proud of. We offer software services training in all aspects of alarm management, and we're based in the UK. So, joining me on this webinar is Levin Dubow. Levin's going to guide us through the webinar. He has almost 40 years of experience in the process industries. He's held a variety of technical, business development, marketing, management and consulting roles. He's been active in alarm management since around 1990. He's a voting member of the ISA 18.2 committee and was elected co-chair of Working Group 8 of that committee. And he's also a qualified instructor for the ISA IC39 course on alarm management. Then you have myself, nowhere near as an exciting introduction as Levin, but I've worked in alarm management for the past 13, 14 years ago for IMAC, for Matricon and for Honeywell. Holding roles in technical support, site engineering, sales and marketing. And I've been the ProcessVue product manager now for Mac Solutions for the last 7 years or so. So what I'll do now is hand over to Levin, who will guide us through the main body of this presentation. If you do have any questions during the presentation, there's two ways you can get those to us. You can either key them into the interface on your screen, or you can also, at the side of your name, I think you can click a little button which raises your hand, and at the end we will be able to unmute you. You'll be able to ask your question to Levin, but that'll be at the end of the presentation. So, okay, over to you then, Levin.
Hello, this is Levin Dubois. Can you hear me?
Yep, we can hear you.
So in this webinar we will talk how to provide enough time for the operator to adequately respond to an alarm. Basically, we will try to provide some answers to the following questions. What is the purpose of timely in the definition of an alarm? How to monitor timeliness of alarms and responses? How much time is available to respond and how much time is required to respond. We will discuss what problems you can encounter when trying to provide more time to respond and what solutions are there to provide more time to respond. If this is of your interest, please continue listening to this presentation. So, why timely? Timely was not present at the ISA 18.2 2009 revision of the standard, where the definition was without this word. The word timely was added by the IEC committee and published in the standard on 2015, and also the ISA 18.2 2016 was updated in this way, as the definition runs today: an audible or visible means of indicating to the operator an equipment fail function, process deviation or abnormal condition requiring a timely response. So what is timely? Timely as such is not defined in the IEC 62682 nor in the ISA 18.2. So you have to pull in the help from a dictionary. For instance, the Cambridge Dictionary says timely is happening at the best possible moment. Fine. What is the best possible moment? Well, EEMUA 191, the guideline on alarm systems, provides a perhaps more precise explanation for this word in the guide. Timely is not long before any response is needed or not too late to do anything. So, what is the best possible moment to raise or enunciate your alarm? EEMUA guideline on page 27, third edition, they elaborate on this subject. They provide this illustration whereby the stars, the yellow stars, represent an alarm. And as you can see in an ineffective alarm system, these stars are in different areas of the operational windows. Actually, some are within the normal operating window, some are in the upset area, others are in the shutdown area. And it's all illustrated that if an alarm is too close to this shutdown area, in the upset area, then there is too short time to respond. So they provide on the same page, in the same figure, the effective alarm systems where all the yellow stars, the alarms, are nicely arranged on the boundary between the normal operating window and the upset area. It looks easy on the picture, but the reality is different. So let's first take a look on what we can find in the alarm and event logs of the alarm's life cycle. You can probably find an alarm that is enunciated in the alarm and event log. You can find probably the time or the event of the operator acknowledging the alarm, and you can probably find the event where the alarm gets cleared. Typically, there is no trace of operator response in the operator log. There are some problems with timing. This is what this webinar is about. You can find in the alarm and event log these things. Alarms that get enunciated and get cleared. They might be too early or too late. The system has cleared the alarm, probably because without any operator action, or it might be that the alarm is fleeting. Then you have this sequence. The alarm gets enunciated, gets cleared, and gets acknowledged after the clear. What happened? Was the operator busy with something else? Did he perform any action or not? We don't know. Is it a way to make the alarm disappear from the alarm display? This acknowledge thing depends on how your alarm system is organized. And then you can find these alarms that get enunciated, get acknowledged, and have no clear. Typically they are called long-standing alarms. The operator action was either inadequate, or the alarm came far too early, or we don't know. The thing might be a defect. Let's try to fix these problems first. An alarm and event reporting tool such as the one from Mac Solutions, ProcessVue Analyzer, can guide you in this matter. You can see here in this diagram that about 62% of the alarms are displayed or enunciated less than 12 seconds. You can ask yourself, what can an operator do in less than 12 seconds? Not much, really. So, anyway, these fleeting alarms or alarms with a very short life cycle, they are distractive. And you also need to investigate whether it's an obligation to acknowledge the alarm. In principle, acknowledging means taking responsibility to deal with the alarm, which brings us to the next slide. This is the alarm response timeline as can be found in the IEC 62682 and the ISA 18.2. But this figure is extended by EEMUA of UCDS with the blue lines to tell a bit more about the operator response delay. So what we have first is the ACK delay. Acknowledge means the operator takes responsibility to deal with the alarm and the imminent abnormal situation to prevent. Or he's going to recover from the abnormal situation, or he's going to mitigate the effects of the situation. Next, you have the operator response delay. The operator should understand what the alarm means. He should think about what to do and not jump to conclusions. We'll have another white paper on that specific subject. He needs to collect all the required information about the situation. He needs to find the right procedure to follow. And he needs to start taking actions or have somebody instructed to perform actions as to go into the plant and do manual actions. Then you have the process dead time. The process dead time is the time the process needs before any effect of the operator action becomes imminent. During this time, the operator should be focused to observe the processes responding to his actions, no distractions wanted. Then up here, you have the process response to the operator action. The operator still needs to monitor the process variable moving towards the clear line. If he's certain and assured this is the case, he might be starting another task, for instance, responding to another alarm. If you start another task, you have to switch between tasks, which means looking at another display, look at the next alarm, and acknowledge and going to deal with it. Keeping an eye on two displays is a kind of multitasking, and as we've seen in the previous webinar, the webinar on KPIs, this is error prone. So what is the maximum operator response time? Is the time between the initiation of the alarm and the consequence threshold, minus the process dead time. As you've seen on this figure, I've drawn two thin green lines to provide a better understanding. So, what is the maximum operator response delay? That is the maximum time the actions can be delayed. Or, how long can the operator wait to start performing his actions? I would call it allowable time, the time the operator can wait to acknowledge, for example, because he is away from his desk or he's performing other tasks, such as dealing with another alarm. So, the maximum operator response time is the time between the alarm is annunciated and the consequence threshold minus the process dead time. Mind you that the consequence threshold is very often set by the safety guys, and if it's not set by the safety guys, it's something to be considered during rationalization. So this maximum operator response time is typically discussed during alarm rationalization based on a number of estimations. Questions to be asked are, can the operator perform all the required actions from his console or desk? Or does somebody need to go into the plant and perform the manual operations? And if that's the case, how big is the distance to get to the right place in the plant to perform these operations? These are all taking time. The other thing to be taken into consideration is the operator response delay. Can an operator immediately, acknowledge the alarm and saying, I'm going to deal with it, or is he still performing another task, just like dealing with another alarm? And another question to be asked, and that's something I'll come back to in one of the next slides, is the operator allowed to be away from his console or his desk? The maximum operator response time is also depending on the process dead time and the consequence threshold. So, and both the process dead time and the consequence threshold should be investigated for that particular situation you want to alarm. So if we do a little bit of mathematics, the ACK delay plus the maximum operator response delay plus the time to perform the actions should be smaller or equal to the maximum operator response time. So we discussed allowable response delay. We need to take the following into consideration. Can we expect the operator to stay the entire shift on the chair in front of the monitors? I don't think so. Can we expect that the operator is only performing one task at a time? I don't think so either. How are you going to manage this? This is not an engineering issue. This is an organizational issue. So, taking the previous rule, you can argue that the acknowledge delay plus the maximum operator response delay should be smaller than the time the consequence threshold is reached, minus the process dead time, minus the time required to perform the actions. I would say the acknowledge delay plus the operator response delay is the allowable response delay. Let's take some examples. Let's say we allow the operator to deal with another task during 10 minutes, or we allow the operator to be away from his desk for 10 minutes, or we have estimated that whatever he's doing might take another 10 minutes before he can adequately take responsibility to deal with the alarm. If you allow that, then this has an impact on your alarm system. Because any possible alarm which requires an operator response in less than 10 minutes should be avoided. Or the operator action should be automated. Meaning that if you find in rationalization such alarm where the operator response delay is less than 10 minutes, that you have to look into, well, when you automate the operator action, then you can decommission or decreate the alarm to something else. And don't forget to document why you have done this. The other option is to establish a new alarm with enough response time. Suppose that your required response time is 5 minutes, and you have 10 minutes allowable time. So in total you have 50 minutes. The alarm limit is set on 20 minutes before the consequence threshold. You're fine. Keep the alarm, document everything that you do, the checks, the procedures, and the actions to follow. And typically those alarms have a low priority. Then the example where you just have enough time, where the required response time is 10 minutes, the allowable response time is 10 minutes, and the alarm limit can set on 20 minutes before the consequence threshold is reached, so there is no way to provide more time. Well, you can still consider keeping the alarm. If the operator is not doing anything else, he can avoid the consequence, and if not, the equipment will trip. Document everything, and perhaps even better, include the procedures or actions in the alarm text so that he doesn't need to look up anything when it gets time critical. Typically, such alarms have a higher priority. So if you have an allowable response delay, then you need to define this somewhere. The alarm philosophy for your site or plant is the place to do it. So allowable time is the time that the operator is allowed to be away from his console for a sanitary break, for getting food or drink, for signing a permit, and so on. So this is an organizational issue, right? It might be that the local authorities dictate such allowable time or away from your desk time. It might be the unions have agreed with plant management to have such a time. So it's not something that is invented by some consultants. No, it's a real thing that happens in real plants because you're dealing with real people and the alarm system is there to support the operator. It's also the time the operator has available to finish or complete another task before responding to the alarm. They should be aware of that. We'll come back to this later. It's also an organizational matter. Basically, if you set up your alarm system in the right way, then you will ask your operator to only acknowledge the alarm when he's capable of starting to assess the situation and perform the required actions. Right? This has some consequences. I think nice buttons like a page acknowledge and so on should be avoided. Also, it should be avoided that people just acknowledge the alarms and do nothing. Like I said, it's an organizational issue, and plant management and human resources should be aware of it because it can come up in discussions. So we want to allow the operator more time to respond to an alarm. So it's very tempting to move the alarm limit, right? So if you start moving the alarm limit, like illustrated in this figure, then there is a chance that you move the alarm threshold into the normal operating window. If you have your alarm limit in the normal operating window, the alarm can be triggered without a proper reason and becomes a nuisance alarm, and then we need to get rid of that. So if you need more time and you want to avoid that it's a nuisance alarm, you need to reconsider your alarm limit. And you will probably find some guidance from your alarm philosophy. If there is no guidance in the alarm philosophy should be reviewed. So what is a potential method to set the alarm threshold at the right place? You have to define the consequence threshold if that is not already defined for you by the safety guys, by the quality guys, or by the authorities. To avoid spills and releases of dangerous substances. Knowledgeable people and operations should estimate the time required to perform the actions. You should estimate or measure the process dead time for that particular situation. And then on top of that, you add the allowable response delay, and then you see where you have to put the alarm threshold. The next thing you need to do during rationalization is to evaluate if this alarm set point, alarm threshold, is not within the normal operating window or in the control range of the control loop. Well, that's... and if it is, then it's time to apply advanced logic. So advanced logic is needed when an alarm limit on a single measured value, a single process value alone, cannot provide enough time to respond to the alarm. What can you do? You can combine, for instance, other parameters from the same process variable from the same control loop, like the rate of change or the direction of change. You can combine process and equipment conditions. Such as are we in startup or shutdown, are we heating or cooling. These conditions are also used to suppress alarms during certain states. You can also use them just to annunciate the alarm in particular states because you know that this is not the normal operating window. You could also use to combine with this alarm set point configurations and status of the control loop. Is the control loop in manual? Is it automatic? Is it cascade? Is it advanced control? What you all have. And for batch processes, you can also take into account the recipe state. For example, rather than alarming that the pH is too low, you maybe add the logic and a message that the control loop is set to manual. The alarm message could then read pH too low and control loop set to manual. Please switch control loop back to automatic and check if the pH value changes in the right direction. This will not only fulfill the requirements of having a timely alarm, but also point to the cause and provide an appropriate action. and herewith fulfill a couple of other characteristics of a good alarm, namely that the alarm becomes diagnostic and advisory. More advanced logic. If a single process value and the parameters of that control loop are not capable of indicating the abnormal situation you want the operator to avoid, then you might need to combine different process variables. So what can you do? You can investigate the alarm and event log for sequence of events leading up to the abnormal situation. This is like a manual search in the alarm and event log. Some tools, like the reporting tool from ProcessVue, can help you in such a search. You could use pattern mining techniques to find such sequences. You can apply data mining techniques to the process historian to predict the abnormal situation and or to find the right contributing variables to that abnormal situation you want to avoid. Note that in such a case you should have such an abnormal situation in your alarm historian. Another thing you can do is to use your simulation model of your plant, which you might use for operator training purposes, and have that run a little bit ahead in time. For instance, you start it every 15 minutes or every 10 minutes and you let it run 30 minutes ahead in time. So if then that simulation hits one of the alarm thresholds, you can say, okay, I have something now that is predicted, and so we have more time to respond. Another thing you can apply is topology reasoning. In a plant, things are interconnected. You have product flows and throughout the plant. So your product flows from one side to the other and is being processed. You have energy flows, how energy is supplied to different devices in your plant. You have also information flows. All these flows have devices and equipments and sensors upstream and downstream. So if you detect the problem, you can predict situations upstream, or you can predict situations downstream. Think of a pump that fails, and you might get alarms downstream because of this failing pump. And you can use such reasoning then to either suppress such alarms or just predict such alarms so that the operator has enough time to respond to those abnormal situations. ISA 18.2 Technical Report 4 offers a number of suggestions in this area. You can download this from the ISA website. If you are a member, you get a discount for this technical report. Okay, let's talk about some of real-world examples of combinational advanced logic. In the first example here, the states of two pieces of equipment are taken into account. If both heat exchangers cannot export enough heat, an intermediate conclusion is made. Yes? This conclusion, combined with an inverse of another state, creates an alarm with a specific request to action. This is an example of combinations of intermediate states which need to be evaluated all the time to maintain persistency. If one of the intermediate states is not maintained, the entire resulting conclusion needs to be withdrawn. The result, however, is an alarm that is advisory of nature as well. In the second example, here we have a direction of a process variable, the suction pressure decrease. We have a state, the suction pressure near low limit, and we have another direction of another process variable, the outlet temperature increase, and all these three are combined. You can predict a compressor trip. So, if you present such an alarm to an operator, the operator should be able to consult the logic, and as with the previous example, the conclusion has to be withdrawn when one of the intermediate conclusions is no longer valid. All these examples are from real plants based on analysis of historical data of those plants almost 10 years ago. In this example, we have results of data mining techniques in the process historian. They come from artificial intelligence techniques on historical data, delivered by Data Maestro from Pepite, a Belgian data mining company. So big data analysis provides a decision tree to estimate the contribution of a number of process values for a given problem. When you bring such decision trees online, they can assist the operator to conduct in a faster way a search for the root cause or to find a measure to avoid the consequence. A resulting alarm should be able to point to such decision tree and show it and highlight the path that is actually current. The fourth example comes from the same source. In this example, a artificial neural network is proposed as a result from the data mining techniques to predict a serious disturbance 30 minutes ahead. This is a bit the same idea as model-based predictions, but in this case you just take a shortcut. Instead of developing a simulation model, you use the artificial neural network. The neural network observes the inputs of a limited set of process variables, each of which is a normal operating window. The output is a predicted process variable, which when triggering the alarm limit and persisting for some time can provide up to 30 minutes more time for the operator to respond. Mind you, with all these techniques, you have to have also logic available which monitors the operating range in which the neural network was trained, because it's only providing sensible information within such a range. So if one or more of these input variables are out of that range, the predictions should be suppressed. So, what are the benefits of applying advanced logic? One of the benefits is to put the alarm at the right time, not too late and not too early, as EEMUA suggests. It's a way to predict an abnormal situation. The abnormal situation is the thing that is beyond the consequence threshold, meaning it can be a trip, hopefully, and not something more serious. If you can avoid that abnormal situation, if you can avoid a trip, like a compressor trip, you also avoid alarm storms. And you address the complaint from the operators that the alarms always come too late. And if they come with an alarm storm. Compressor has tripped, and then you get a bunch of other alarms as a result of that trip. And the side effect is that you improve the quality of the alarms such they become more diagnostic and advisory. Now, if you want to implement this, the IEC 62682 standard suggests that you shall train the operator. It's an obligation. So first of all, you need to train the operators to understand the alarm philosophy if you have put the concept of allowable time and advanced logic in your alarm philosophy. You should train the operators to understand any advanced logic when it is applied. And you should, the operators should understand that such logic is to their benefit. It is suggested by EEMUA 191 that such logic should be presented in a graphical way and not in like programming code of any kind, in order that the operator understands the logic that is applied to generate the alarm. Eventually, if your HMI allows it, you should make perhaps a help function in your alarm such that the operator can view the logic that has triggered the alarm. But that's a general recommendation. That's a bit outside the scope of this webinar. Another thing to take into consideration when applying advanced logic is that it needs to be tested before being put in operation. How can you test it? Well, you can replay a number of situations from the past and see if it triggers, and also test if it doesn't trigger unnecessary. Like already said in the slide on the neural network, you have to monitor carefully the conditions during which predictions can be made. It makes no sense to enable such advanced logic for during startup and shutdown and so on when it's not applicable. And you should also monitor and evaluate advanced logic regularly, which brings us to the next slide. So your alarm reporting and assessment tool should help you in this way. The alarm reporting tool should illustrate that there are less alarms. It should illustrate that there are less alarm storms because you avoid the alarm storms, you avoid the consequence threshold. And if you do it well, you can also evaluate if there is more time for the operator. Mind you, if you are going to say 1 alarm per 5 minutes and move towards 1 alarm per 20 minutes, you have more time for the operator, right? The alarm monitoring and assessment tool should also evaluate what alarms are being shelved. If you can derive from the reporting that the alarms that are generated by advanced logic are shelved, then there might be something wrong with your advanced logic. The other thing you can use your alarm reporting and assessment tool for is to monitor how the operators acknowledge the alarms. Is it always within milliseconds after they appear? If so, well, then it's perhaps because they've put a coin on the acknowledge button or a battery on the acknowledge button. Like normally it's impossible to be consistent in acknowledging in milliseconds. Is it always on the edge of the allowable time? Does it mean that they just wait the 10 minutes they are allowed to wait before they acknowledge? It's not the right attitude either. Or does this acknowledge time varies with the workload? At that point, if the acknowledge time varies with the workload, it can tell you something about the workload for the operator. So, next to monitoring and assessing with a tool, which is something you can run on the background and reports automatically every week, every 2 weeks or every 1 month, there is, as proposed by the standards, the audit process. The audit process verifies the perception of the operator. So the audit process must include operator interviews, and one of the questions to be asked is, are the alarms now coming on time? Is that to the perception of the operators, are they on time or are they not on time? Is the applied logic working or is it becoming a nuisance? Do you have enough allowable time? It might be that you start off with an allowable time away from your desk from 5 minutes, and the operators say, okay, that's an enormous improvement, but they are assigned other tasks to do, and they say, well, we don't have enough time anymore, so we need more allowable time. In that case, you need to update the alarm philosophy, and you can say, okay, we're going to introduce more or less allowable time, or we're going to allow more or less advanced logic in our design of our alarms. This brings me to conclusions. The alarm philosophy is the place to define the allowable operator response delay, or the maximum act delay. Depends on how you call it in your alarm philosophy. Good timing requires a consensus in the alarm philosophy on an acknowledgement strategy. Think about acknowledge only if you as an operator are going to do something about the situation being alarmed. no longer acknowledge after the alarm is cleared, removing the page acknowledge button from the alarm display. Good timing requires also consensus in the alarm philosophy to apply advanced logic or not. Good timing requires a rationalization process which provides figures or estimates in process dead time, and the rationalization process which discusses and estimates the time to perform the actions and to assess the alarm situation. Good timing requires a design process that is capable of testing and validating the advanced logic, and an implementation process that includes the operators and train the operators in this new way of predictive alarming. Good timing requires a monitoring and assessment process and tools that are capable of measuring the acknowledgements and the clear times. Mind you, most of the alarm logs do not contain operator actions in that logging, because an operator action can be a telephone call or a manual operation which you have no trace in the alarming event log. Finally, good timing requires an audit process that provides required feedback from operations. So, when the organization agrees that acknowledging alarm actually means starting the task of dealing with the alarm, the acknowledge delay can be used for measuring and assessing this allowable time. Remember that timely alarms are for the benefit of the operators, not to overload them. Timely alarms will help restore the confidence the operator has in the alarm system. And lastly, timely alarms will help to avoid downtime, outage and damage, which means money. So basically, if you implement the right and appropriate response times, you can avoid the consequences or mitigate the consequences of abnormal situations properly. So, what I would like you to take away from this webinar is why timely was added to the definition of alarm in IEC 62682 and ISA 18.22 2016, how to monitor timeliness, how to think about time available, how to provide more time to response, and what the benefits are of timely alarm. And thinking of that, are your alarms coming on time? Thank you for your attention. If there's any question, please raise your hand in the webinar tool, or type in the question in the chat session, or something else. Jason, over to you.
Okay, thank you very much, Levin. So yeah, I think it's really interesting now, the introduction of just one word, namely timely, makes a huge difference to how you should think about and rationalize your alarms. Really interesting. Thank you. So yeah, we'll open up to any questions people may have now. So there's a couple of ways you can do that. You can raise your hand and I will unmute you and you'll be able to ask your question directly, or you can type into the questions section on your screen as well and do it that way. We don't currently have any questions at all, so just give you a few seconds just to see if there are any questions there that you'd like answering. Just while we're waiting then, there will be a white paper available. I think it's now live on the ProcessVue.com website. So there's a web paper up there on timely alarms, along with a lot of other white papers as well. Also, if you go on the ProcessVue.com website, in the resources menu, you'll see links to the videos of previous webinars and other resources there as well, which are all free for you to use. So there are no questions. So what we'll do is we'll close down the presentation now. Thank you all very much for attending. We'll be in touch soon with the next webinar in the series for a date for you on that. And we look forward to seeing you then. Okay, thank you very much, guys. Goodbye.